Water that comes from natural sources, such as lakes and rivers, often contains dissolved solids and dissolved gases. If they're not removed, these dissolved materials can cause problems in plant equipment. Dissolved solids and dissolved gases are removed from water by a process called secondary water treatment. If large amounts of solids are dissolved in water, the water may become highly alkaline. Highly alkaline water can cause corrosion, which is a chemical attack on metal surfaces. Other problems associated with dissolved solids occur when the dissolved solids come out of solution and form scale or sludge. Scale is a solid coating that can form on the insides of pipes and equipment, and sludge is an accumulation of solids that have settled and formed a thick mixture. Scale and sludge can form inside pipes and equipment and reduce their capacity. Scale and sludge can also reduce the efficiency of heat transfer in equipment. The amounts and types of dissolved solids that water contains depend on several factors. One of these is the temperature of the water. Typically, the higher the temperature of water, the more dissolved solids it can hold. Another factor is the solubility of the solid, that is, how much of the solid will dissolve in water. Some solids dissolve more readily in water than others. If the amount of solids dissolved in water exceeds the amount of solids the water can hold, precipitation will occur. In other words, the solids will come out of solution. Since higher temperature water can hold more solids than lower temperature water, precipitation is most likely to occur when water is cooled. Another physical change that results in the precipitation of dissolved solids is evaporation. Evaporation is a process in which the heat in water causes part of the water to turn into a vapor. As the water evaporates, the dissolved solids become more concentrated in the water that remains. Eventually, the water can't hold all of the dissolved solids and precipitation occurs. The mixing of water from two or more sources can also result in precipitation. Water from different sources usually contains different dissolved solids. When mixing occurs, a chemical reaction between the different dissolved solids can form an insoluble material which settles out as precipitate. One piece of equipment that's commonly used in secondary water treatment to remove dissolved solids is a water softener. Water softeners are designed to remove dissolved solids such as calcium and magnesium salts. When these solids are dissolved in water, they separate into electrically charged particles called hard ions. Water that contains a lot of hard ions is referred to as hard water, and hard water produces scale. Water is softened by a process called ion exchange. In a water softener, hard ions are exchanged for soft ions, such as sodium ions, which normally don't cause scale. This is an illustration of a typical water softener. It includes a tank or shell and a resin bed made up of small plastic beads called resin beads. The resin beads are porous so that water can pass through them. During operation, hard water enters the softener through this inlet and passes through a device called a diffuser. The diffuser spreads the water out to ensure an even flow through the resin bed. Each bead in the resin bed has thousands of charged areas called sites. In this example, each site is occupied by a sodium ion, which is a soft ion. When the water contacts the resin beads, the calcium and magnesium ions in the water, the hard ions, compete with the sodium ions to occupy the charged sites. The hard ions have a stronger attraction to the sites than the sodium ions. Because the hard ions have a stronger attraction to the sites than the sodium ions, they replace the sodium ions on the resin beads. This exchange of ions occurs because of a property called selectivity. Selectivity means that different ions have different degrees of attraction to the resin bead sites. After the hard ions in the water have been replaced by the sodium ions, the softened water is collected in an under-drain system and leaves the softener. Over time, magnesium and calcium ions build up on the resin beads in the softener. To remove these hard ions so that the resin beads can be reused for softening, a process called regeneration is performed. During this process, the hard ions on the resin beads are replaced with sodium ions. Generally, regeneration takes place in 3 steps: backwashing, regenerating, and rinsing. During backwashing, water is pumped into the softener through the water outlet. As the water passes through the resin bed, it carries any suspended solids that are trapped among the resin beads out of the softener through the water inlet. In the next step, regenerating, a concentrated saltwater solution is passed through the resin bed. The overwhelming number of sodium ions in the salt water solution overcomes selectivity. The sodium ions drive the hard ions off of the resin bead sites and replace them. Finally, in the rinsing step, rinse water enters through the water inlet. Rinsing removes the remainder of the salt solution and the hard ions from the softener. The rinse water drains out of the outlet and is pumped to a treatment facility. The extremely pure water that is needed for some processes can be provided by demineralizers. Demineralizers use resin beads to replace many different types of ions with ions that combine to form pure water. Positively charged ions are called cations, and negatively charged ions are called anions. Cation resin beads are used to remove cations such as calcium, magnesium, and sodium ions. The cation beads initially have positive hydrogen ions attached to their sites. Anion resin beads are used to remove anions such as chloride, sulfate, and carbonate ions. The anion beads initially have negative hydroxyl ions attached to their sites. In this illustration of a demineralizer, this tank contains cation resin beads. The other tank contains anion resin beads. During operation, water enters the first tank and passes through the cation resin bed. The cations in the water compete with the hydrogen ions for the resin bead sites. The cations replace the hydrogen ions on the resin beads, and the hydrogen ions are released into the water. With the cations removed, the water is sent to the second tank. As the water passes through the anion resin bed, ions are exchanged again. The anions in the water replace the hydroxyl ions on the resin beads, and the hydroxyl ions are released into the water. Now the water contains mostly hydrogen ions and hydroxyl ions, which combine to form pure water. Over time, cations and anions build up on the resin beads. To remove these ions, the resin beds must be regenerated. This is typically accomplished in 3 steps. First, backwashing the beads in both tanks flushes out suspended solids. Next is the regenerating step. An acid is sent through the cation resin bed, and the concentrated hydrogen ions in the acid replace the cations on the resin bead sites. The anion beads are regenerated with an alkali. The concentrated hydroxyl ions in the alkali replace the anions on the resin bead sites. Finally, both beds are rinsed, and the rinse water is sent to a treatment facility. In this topic, we looked at how dissolved solids in water can affect plant equipment. We also saw some of the devices used to remove dissolved solids from water. Now try some practice questions to check your understanding of this material. Scale and sludge can form inside pipes and equipment and reduce their capacity. Scale and sludge can also reduce the efficiency of heat transfer in equipment. The amounts and types of dissolved solids that water contains depend on several factors. One of these is the temperature of the water. Typically, the higher the temperature of water, the more dissolved solids it can hold. Another factor is the solubility of the solid. That is, how much of the solid will dissolve in water. Some solids dissolve more readily in water than others. If the amount of solids dissolved in water exceeds the amount of solids the water can hold, precipitation will occur. In other words, the solids will come out of solution. Each bead in the resin bed has thousands of charged areas called sites. In this example, each site is occupied by a sodium ion, which is a soft ion. When the water contacts the resin beads, the calcium and magnesium ions in the water, the hard ions, compete with the sodium ions to occupy the charged sites. With the cations removed, the water is sent to the second tank. As the water passes through the anion resin bed, ions are exchanged again. The anions in the water replace the hydroxyl ions on the resin beads, and the hydroxyl ions are released into the water. Now the water contains mostly hydrogen ions and hydroxyl ions, which combine to form pure water. The major problem associated with dissolved gases in water is corrosion. Basically, corrosion is a chemical attack on metal surfaces that leads to a loss of metal. Some of the more common dissolved gases found in water are oxygen, carbon dioxide, and hydrogen sulfide. Dissolved oxygen combines with iron to form rust, and dissolved carbon dioxide and hydrogen sulfide form acids that may corrode plant equipment. The types and amounts of dissolved gases found in water depend on several factors. Typically, the higher the pressure on a gas, the more it is absorbed by water. Also, the lower the temperature of the water, the more gas it will absorb. In addition, different gases dissolve in water at different rates. Dissolved oxygen gets into water from air contacting the water. Carbon dioxide also dissolves in water from the air, but it can come from other sources as well. One source is decaying plants and animals. Another source is the breakdown of a carbonate mineral in aquifers. Aquifers are beds of water-carrying rock. The carbon dioxide dissolves into the aquifer's water. Sources of hydrogen sulfide include decaying plants and animals and aquifers that are near petroleum or natural gas deposits. One of the most common ways to control corrosion is to remove dissolved gases from water. Water can be heated to remove dissolved oxygen, and chemicals can be added to make water less acidic. Sometimes corrosion can be prevented by using materials such as plastic and stainless steel, which do not corrode under ordinary conditions. However, plastic may not be suitable for some high-pressure situations, and stainless steel may be too expensive to be practical. In some instances, tanks and other equipment are lined with materials such as plastic or cement, or corrosion inhibitors are applied to steel to minimize corrosion. These materials form a corrosion-resistant barrier between the water and the surface of the metal. Activated carbon filters are often used to remove some types of dissolved gases from water during water treatment. For example, chlorine gas is sometimes added to water to kill organic contaminants, and a certain amount of chlorine may be retained in the water to make it safe to drink. However, it is frequently necessary to remove dissolved chlorine gas from water so that it will not interfere with water softening or with chemical reactions. Here's an illustration of a filter. It contains activated carbon granules. Each granule has a complex network of tiny openings or pores which give the granule a lot of surface area. The granules form a porous bed that traps impurities such as chlorine gas, some suspended solids, and some dissolved organic solids. The carbon granules are supported by an additional layer of filtering material, typically sand or gravel. This filter uses pressure created by a pump to force the water through the activated carbon granules. As the water passes through the activated carbon, the chlorine molecules are attracted and become attached to the surfaces of the carbon's granules. The water then flows out of the filter to be used or treated further. Aerators are used in secondary water treatment to remove dissolved gases such as hydrogen sulfide and carbon dioxide. The dissolved gases are replaced with air. This is an illustration of a typical aerator. Water enters the aerator through an inlet and falls onto a distribution tray, which breaks the flow of water into many small streams. The water then falls through several levels of staggered trays, which further break up the flow and increase the water's surface area. A blower forces air up through the streams of water. As a result, the water becomes saturated with air, which is mostly nitrogen and oxygen. The air replaces the hydrogen sulfide and carbon dioxide, which are almost completely removed or stripped from the water. The stripped gases and the excess air flow through air stacks in the distribution tray and out of the air outlet. The water flows through an air seal to the water outlet. The air seal prevents air from blowing out through the water outlet. In some circumstances, water containing even small amounts of dissolved gases may lead to problems such as corrosion. One piece of equipment that's used to remove dissolved gases, such as oxygen, is a deaerator. During operation, water is sprayed onto trays in the deaerator that break the water up into small droplets. Steam is fed into the deaerator, and the water droplets are heated as they cascade down through the trays. The trays help lengthen the period of contact between the water droplets and the steam. The deaeration process strips away most of the dissolved oxygen and other gases in the water. The released gases collect at the top of the deaerator and are vented off through a vent line. The deaerated water falls into a storage tank. In this topic, we looked at some of the devices used to remove dissolved gases from water. We saw examples of an activated carbon filter, an aerator, and a deaerator. Now's a good time to check your understanding of this material. The major problem associated with dissolved gases in water is corrosion. Basically, corrosion is a chemical attack on metal surfaces that leads to a loss of metal. This filter uses pressure created by a pump to force the water through the activated carbon granules. As the water passes through the activated carbon, the chlorine molecules are attracted and become attached to the surfaces of the carbon's granules. Aerators are used in secondary water treatment to remove dissolved gases such as hydrogen sulfide and carbon dioxide. The dissolved gases are replaced with air. During operation, water is sprayed onto trays in the deaerator that break the water up into small droplets. Steam is fed into the deaerator, and the water droplets are heated as they cascade down through the trays. The trays help lengthen the period of contact between the water droplets and the steam. One use of chemicals in water treatment is to remove or neutralize impurities. For example, chlorine is used to kill microorganisms, and chemicals can be used to add desired properties to water. For example, corrosion inhibitors are chemicals that are sometimes added to minimize corrosion. One type of corrosion inhibitor works by forming a protective film that sticks to metal. Another type of corrosion inhibitor is an oxygen scavenger. Oxygen scavengers react chemically with dissolved oxygen to form a compound that isn't corrosive and won't cause scale. There are also chemicals called scale inhibitors that protect equipment from scale formation. Some scale inhibitors form a protective film on surfaces. Others react with scale-forming compounds to form compounds that won't stick to the inside surfaces of pipes and equipment. Another example of the use of chemicals in water treatment is to make pH adjustments. This means adjusting the acidity or alkalinity of the water. Water with a low pH, that is, acidic water, speeds up the corrosion of metal surfaces. Water with a high pH or alkaline water leads to scale buildup on the inside of pipes and equipment. An acid, such as sulfuric acid, or an alkali, such as lime, is sometimes added to water to adjust the water's pH. Chemicals can be added to water in a variety of ways. For example, this is a chemical injection pump. A chemical is stored in this tank and fed to the pump. A stroke adjustment is used to adjust the rate at which the chemical is fed into the water. Adjusting the stroke lengthens or shortens the stroke of a piston inside the pump. A longer piston stroke increases the rate at which the chemical is injected, while a shorter piston stroke reduces the chemical injection rate. Many of the chemicals used in water treatment can be hazardous if they're not handled properly. You need to be aware of the specific dangers associated with the chemicals you work with and know how to protect yourself from them. Before you handle any kind of chemical, read the information on the label or its material safety data sheet, and, if necessary, ask a supervisor about it. Always follow your company's procedures for handling chemicals and responding to an accidental spill. Know where the eye wash stations and safety showers are located in your work area. Make sure they're in good operating condition and that you know how to use them. If the chemical is especially hazardous, or if the task you're doing is new to you, you should work with an experienced person. You can also help protect yourself by wearing the appropriate safety equipment. For example, you'll need respiratory protection and goggles to protect your nose, lungs, and eyes when you're working with dusty chemicals such as lime. You may need a face shield to protect your eyes and face from chemical splashes. You might also need rubber gloves, boots, and an apron. If an acid or alkali is splashed on your skin or clothing, or if your eyes are splashed with chemicals, quickly get to the nearest emergency shower and eye wash station. Rinse the affected area for several minutes to make sure that the chemical is completely diluted and washed away. To rinse your eyes, keep them open and directly in the flow of water for 15 minutes. Always report any accident, regardless of how minor it is. When describing an accident to someone on the phone, be sure to state your name, your location, and the type of accident that has occurred. In this topic, we looked at how chemicals can be used in water treatment. We also looked at a very important part of working with chemicals, safety. Now try some practice questions to check your understanding. Another type of corrosion inhibitor is an oxygen scavenger. Oxygen scavengers react chemically with dissolved oxygen to form a compound that isn't corrosive and won't cause scale. If an acid or alkali is splashed on your skin or clothing, or if your eyes are splashed with chemicals, quickly get to the nearest emergency shower and eye wash station. Rinse the affected area for several minutes to make sure that the chemical is completely diluted and washed away.